Alright, hello everyone. Hope you guys are doing good today. Remember, hit that like button, smash subscribe now, or else I'll fail you. So today we're going to look at entropy, alright? And it's going to be our second thermodynamic term. So we looked at enthalpy, right? Delta H, looking at the potential energy difference between bonds, the products versus reactants. And today we're going to look at entropy. Okay, so entropy can be thought of as the measure of the disorder of the system. Or just the measurement of disorder. Okay, so this is really what we're looking at. So a higher entropy value means there's a greater disorder. A lower entropy value, so entropy, which is represented by an S. So if my value is higher, we have more disorder. And if my S value is lower, we have less disorder. Okay. So that's what we're going to be looking at. And really what this is based on is this disorder is based on microstates. Okay, so it's this idea that, say I've got this cylinder here. I've got three gas particles or three particles, okay? So they could be right here. That's one arrangement. Or, you could have them like this over here. Or maybe this one moves over here. So there's two arrangements where there's two on one side and one on the other side. Or maybe this one comes back to here. It's kind of hard to do. I should have. And then that one moves over there. So just right there. So, with that arrangement, there's multiple ones. And so the more particles you have, the more disorder you have, or that's kind of what it's looking at. Okay, so disorder based on microstates. All right. So the reason this came about is this idea of why do reactions happen? Right. What makes a reaction happen, or why does it happen? They initially thought that enthalpy drove all those things, but the problem with that is that we've seen that some endothermic reactions happen. So there's this other term that they came up with, entropy, okay, or this other phenomenon they noticed. And what they noticed is that for all thermodynamically favorable processes, I didn't spell that right. Give me a second. Thermodynamically favorable processes, that the entropy of the universe is increasing. So some key terms right here, thermodynamically favorable. Okay, that's going to mean it happens. Okay, this idea that what happens? Well, if it happens, it's thermodynamically favorable. If the reaction doesn't happen, it's not thermodynamically favorable. Okay? And that's the verbiage that AP likes to use. So we'll abbreviate it as TDF. So I don't have to write that out every time. Thermodynamically favorable. Okay. So in other words, it's saying that as the process happens, what happens is there's more disorder in the universe. Okay, the disorder of the universe is always increasing, and this is the second law of thermodynamics. Okay, that the disorder of the universe is increasing for a thermodynamically favorable or irreversible process. Right? So, some stuff that we'll notice, the difference between enthalpy and entropy. Okay, so first off, when we were measuring enthalpy stuff, if you looked in our tables, we always had these delta H of formations. Okay, well, enthalpy has no zero value, right? We were saying it's all relative. Okay, this is not true for entropy. So delta S or S has an absolute zero. Okay? Or something that's completely ordered, right? If S is a measurement of disorder, then a zero would be when is it completely ordered? And it's completely ordered in a crystalline solid at 0 degrees or 0 Kelvin. Okay, so if something is said to be perfect order, so crystalline solid, it's all structured perfectly, and 0 degrees Kelvin means there's absolutely no movement. And that's my 0 point for entropy. All right? And this is the third law of thermodynamics. All right, so let's get to the examples and kind of look at what do we mean when something increases or decreases in disorder. All right, first off, let's talk about phase changes. All right, if something goes from a solid to a liquid, what happens to the disorder? Well, when you have a solid, you have those particles that are what? They're rigidly stuck right next to each other, correct? Okay, they're formed, they're not going anywhere, they're stuck. All right, so pretty ordered. The disorder would be low. When we go to a liquid, now those particles are still next to each other, but now they're free to kind of move around, and I don't know if that's the best drawing. Looks pretty ordered, so they can move. All right, there's more arrangements that they can be in a liquid than there are solid. Solid, they're fixed. Liquids, they're starting to, they're now mobile here. So what would we say? Well, the disorder increases. Therefore, the change from solid to liquid, so that delta S is greater than 0. Right, and increases in disorder. Let's look at another phase change. What if we go from liquid to gas? Okay, so again, we have our mobile particles floating around next to each other, but still close to each other. When they go to the gaseous phase, now where are they? They're very far apart, right? Moving randomly. Okay, so what would we say about this? Well, again, this is much more chaotic, right? Because they're not right next to each other. There's infinite number of positions they could be even in between each other. So my disorder increases again. So my delta S is greater than 0. Okay, my gases are always going to have more disorder than solids. Okay. When looking at the change in disorder or the change in entropy, a phase change often causes the largest, or is, I'm going to say is the largest factor for determining the delta S. And I cannot write today. Okay. So phase changes are going to be really important in a chemical reaction. So let's take a look at what I'm talking about here. Let's say I have some 2 moles of liquid water. Okay. And I'm going to do a decomposition. It's going to go to 4 moles of H2 gas. Sorry, 2 moles of H2 gas plus a mole of oxygen gas. Okay, so if I do that decomposition, I'm going from 2 moles of liquid to 3 moles of gas. So in this case, my delta S would be very positive. Why? Because I'm going from a liquid to a gas, phase change, and then also we're going from 2 moles of liquid to 3 moles of a gas. So a large, we're really increasing the amount of disorder on this side of the system. Let me get another example here for you guys. So let's take a look at this equation right here. If I have 6 moles of carbon solid plus 3 moles of hydrogen gas, and it goes to a mole of of C6 liquid. Okay, let's predict the sign for delta S in this case. All right, so first off, I'm going from 9 total moles, 6 of them solid, 3 of them gas. And here's the big thing. We're going from a gas as a reactants to liquids as a products, right? This is a big deal right here. This is a massive decrease in the disorder, right? Liquids are much more ordered than gases. So my delta S in this case is going to be less than 0 or negative. It's going to decrease the disorder of the system. All right. The other factor that we have to look at when we're doing this is total number of moles. So of products and reactants. Okay. So an example of this is, think of when there's going to be more disorder. Let's say you're babysitting, all right? And you have 2 toddlers, right? Toddlers, I have a couple. I have one, I guess, right now. They're crazy, right? They run around, they make chaos, they leave toys and stuff everywhere. So 2 toddlers, kind of crazy. Well, if I increase it to 4 toddlers, right, it would be even what? The disorder would increase. Even though they're in the same phase, right, as a toddler, phase change. But the amount of toddlers you have would increase the disorder. So let's look at a reaction where there isn't a phase change, but let's look and see how moles of products and reactants would affect delta S. So here's our reaction right here. 2 moles of NH3 gas plus 3 moles of O2 gas plus 2 moles of C4H gas goes to 2 moles of HCN gas plus 6 moles of water vapor. All right, so first thing, if we're going to predict delta H for this reaction, what we notice is there's no phase changes, right? Okay, phase changes are always going to be one of the most important thing to look at. But we have gases as reactants and we have gases as products. So the next thing we're looking at is total moles. So I have 2 plus 3, so 5 plus 2 more. So I've got 7 moles of gas on this side. And on this side I have 2 plus 8, there's 6, so I have 8 moles of gas on this side. Right? So I've increased the amount of moles of gases, so therefore my delta S is going to be greater than 0. My disorder has increased. Okay. All right, so there's a look at our intro into entropy. Okay, so if we remember, entropy is the measurement of disorder of a system. Okay, as the disorder increases, the S is going to be increase. As the disorder decreases or something becomes more ordered, the S is going to decrease. All right. Hope you guys have a good day.